Hi. So I'd like to start by telling you a little bit about who I am and why I'm here. My name's Troy. I'm a software engineer at Hex-Rays. I've been with them for about 5 years now, and I focus mainly on the Mac-specific features of IDA Pro. That includes the iOS debugger, the OSX Debugger, Objective-C plugin, and lately I've been working a lot on the decompiler, trying to improve Objective-C decompilation. But today, I'm going to be talking about a little project I've been working on for the iOS debugger. So the purpose of this talk is mainly to share what we found. We've discovered a way to communicate with a secret server running on iOS, and I mean, when I say secret, I just mean it's not explicitly documented and not normally available to people outside of Apple. So if you're interested in iOS internals, this is the talk for you. We also wanted to just simply walk you through all the steps that we took to achieve our goal. This wasn't the first time someone's reversed iOS internals, and it won't be the last. So it's likely that even the little steps will help other people working on similar projects. But most of all, this is just plain old fun. This wasn't your typical progression of commercial software development, and we think you might find that pretty cool. So first, I'd like to explain what the instrument server is and why we care about it. Instruments is a set of debugging tools developed by Apple, and they allow you to, for a given app, they allow you to do very specific debugging tasks. For example, you can profile your app, you can check for memory leaks, you can track file I/O, you can monitor memory, CPU usage, a lot of very useful things. And all of these tasks can be performed on iOS apps as well. And the way Apple does this is they implement an instrument server that's designed specifically to feed all this debugging info to the instrument's front end running on OSX. So to Hex-Rays, a company that develops its own iOS debugger, this server is a goldmine of useful information, and we want access to it. So watch out, instruments. Hex-Rays is coming for you. So here's a little simple diagram of the system we're dealing with. We have the instrument server running on iOS, and the instrument's front-end tools like Xcode and the time profiler and all that running on OSX. Somehow they communicate. So now the burning question is, how exactly does the server transmit all this valuable information to OSX? And more importantly, how can IDA tap into that? So this is a pretty complex and maybe daunting task. Where do we even start? So we noticed that for most of Apple's debugging tools, you can attach to a process running on your device. It's very likely that the instrument server is responsible for fetching the process list on your device and transmitting it back to Xcode. This is interesting to us because we want to implement the same functionality in IDA. So if we could somehow reverse engineer the logic that fetches the process list, number one, we'd be able to figure out how the server works, and number two, we'd also be improving IDA as well. So we thought this would be an excellent place to start. So, how do we fetch the process list from the iOS instrument server? Well, somehow we're going to have to communicate with an internal iOS process, which normally is not allowed. You can do it if you jailbreak your phone, but if you want to play nice, you have to go through the mobile device framework. And mobile device provides the ability of OSX apps to communicate with certain iOS processes that Apple likes to call services. This is how IDA communicates with the iOS GDB server. So, if we're lucky, there's also a service for the instrument server as well. How do we tell? And the answer lies in this file. So this is a plist that is included in the iOS Developers Tools package. And what it tells us is that the instrument server is published as a service that we can connect to the same way we would the debug server. So this is good news for us. It checks off two important sanity checks. One is that we can at least transmit bytes to the server. It won't have any idea what we're talking about, but at least it can hear us. And number two is that we know which binaries to analyze in order to reverse engineer the server's logic. So from this file, we can tell that the core functionality of the server is implemented in a framework called DVT Instruments Foundation. And in this framework, we find an interesting method called running processes. It appears to be exactly what we're looking for. it populates an array with a description of each process and returns it. So we suspect that Xcode somehow sends the instrument server a command telling it to call this method and then transmit the result back to Xcode. So it looks like we're on the right track, but this method actually isn't called anywhere. There's no cross-references to it, and in fact, the string running processes appears nowhere else in the iOS developer tools. So who calls this thing? Well, the best way to check is to set a breakpoint. So what I've done here is launched IDA and told it to attach to the instrument server process running on my phone and set a breakpoint at the running processes method. So if our theory is correct, we should be able to trigger this breakpoint by asking for the process list in Xcode. And it's hit. So there's some good news. Let's figure out exactly how it was called. So the first thing we notice is that it was not called by Objective-C message send, as it normally would for a normal Objective-C method. It was called indirectly by an NS invocation object. And a quick Google search tells us that an NS invocation is just a different way of calling an Objective-C method. And this NS invocation was created by something called a DTX message. And this class ends up being our first really big clue. So if we take a closer look at the DTX message class, we see that it's responsible for serializing and deserializing Objective-C messages. So that means an instance of this class can somehow encode all the information necessary to call an Objective-C method. So if you want to call a method, you need a method selector, or the method name, some arguments, and the object that implements the method. So DTX message can serialize all this information and spit out some raw data. And the reverse direction is also possible. DTX message can parse serialized bytes, resolve them into Objective-C objects, and use that to invoke a method. And this is exactly how the instrument server is invoking critical logic. It reads serialized messages from a buffer, and then parses them, and then performs the invocation. So now the question is, who is doing the serialization? Where are these serialized bytes coming from? So this all starts making a little bit more sense if we look at the binaries for the Xcode IDE. In there we find this interesting bit of code. It's not trivial, but the important thing is we found our running processes selector. I was looking everywhere in the server's code for this, because after all, it's the name of a method implemented in the server, but here it shows up in the client's code. That's interesting. So it looks like this bit of code might be the key to understanding what's going on here. So let's take a closer look at it. What we're actually looking at is a decompiled block function. If you're not familiar with block functions, they're basically Apple's implementation of an anonymous function or a lambda function. And you can see here that it's toward the end of the code snippet there, our block function appears denoted by a caret, and it's enclosed in braces, the function definition. This looks a lot like we're serializing a method call. We're creating a DTX message, passing it the selector, running processes, and passing null for the arguments, since running processes takes no arguments. And then we're using something called a channel to transmit this message to a server, to the instrument server. So there's a lot of unanswered questions here, but we can make one important conclusion, and that's that this DTX message class provides the ability to transmit Objective-C messages over the wire. So this allows a process to effectively call a given method in another process that could be running on a totally separate device. So I was not expecting that at all. I was hoping for something much more primitive. I was hoping that Xcode was somehow sending some request code to the server, telling it to call some method and then transmit the result back with some simple serialization. But Apple's solution is much more general. It looks like I'm going to have to be able to remotely invoke Objective-C messages or methods and transmit arbitrary Objective-C objects over the wire, which is a whole nother level of interoperability that I wasn't ready for. So now it feels like I'm kind of getting in over my head. It's possible to reverse engineer the format of these serialized messages purely from the disassembly, but this will be hard. The code is extremely Objective-C heavy. Apple completely abuses their use of these lambda functions or anonymous functions, and those two together kind of form their own layer of obfuscation that we're going to have to deal with. And even if we understand message serialization perfectly, it still doesn't tell us the whole story. What if the server only responds to a specific sequence of messages? It's hard to tell just from the disassembly. So an alternate approach would be to obtain samples of the raw data transmitted between Xcode and the server. This would give us a very detailed but also very high-level overview of what a conversation with the server might look like. So we did just that. I developed an IDA plugin that will automatically log every message that the server receives. It's free to download for anyone. It's from my GitHub page, username Troy Bowman /DTXMSG. And the plugin uses the decompiler's microcode to detect when and where serialized data is available in memory and dumps the bytes to a file. So if you're curious about the microcode, Ilfak did a nice talk about it earlier this year at Recon Brussels. So if this plugin interests you, you might want to check that out as well. It turns out the microcode is super useful for analyzing Objective-C, and we're taking advantage of that here. And the plugin can also deserialize each intercepted message and print the results to a file in plain text. And we'll cover more on that later, but for now, let's just log the raw data. Oops. So let's try it. So what I've done here is launched IDA with the DTX message plugin. It will analyze the instrument server's code, find some critical logic in it, place breakpoints at that logic, and whenever one of these breakpoints is hit, a message is logged. So if we query the process list from Xcode, we should see that our plugin intercepted some messages here. Let's check them out. So we see that our plugin intercepted 5 messages. Maybe one of those is our magic running processes method. Let's check. So if we grep for the string running processes, one of our files matches. That's great news. So apparently, this is a serialized Objective-C message. Let's take a closer look at it. So the first thing we notice is that the first D word is a value that shows up all over the server's code. This is a magic value that signifies the beginning of a serialized Objective-C message. That's a great sanity check for us. And here we have our running processes selector showing up, surrounded by a bunch of junk that we don't understand. But we do find another clue, and that is the string ns-keyed archiver. And another quick Google search tells us that this is just a class designed specifically for serializing Objective-C objects. So it looks like the method selector is being serialized with this ns-keyed archiver class. So that takes care of the method selector. What about the method arguments? Running processes takes no arguments, so that won't be much help to us. So we did intercept a different message with a different selector, installed applications matching blah, blah, blah. We have no idea what this means, but from the 2 colons in the selector, we can tell that it takes 2 arguments. And, not coincidentally, we have 2 separate archived objects showing up in this intercepted message. So it looks like the method arguments might be being serialized by this ns-keyed archiver class as well. So this is starting to make a little sense here almost. But there's still one important detail that we're missing, and that's the message receiver. Who decides which object will receive this message? So remember that in Xcode's code, we saw that it uses something called a channel to transmit the bytes to the server. And these channels are created using some kind of unique identifier. But it turns out that we intercepted a message that contains that exact same identifier, and it looks like it's being passed as an argument to a method request channel with code and identifier. That ends up being a really important clue, another one. So that was a lot to digest, so let's review. When querying the process list, Xcode sent 5 messages to the instrument server. Turns out these 2 simply just fetch a list of all installed applications on the device. That's interesting, but it's not totally necessary for what we're doing here. These 3 messages are likely the minimum required interaction with the server to get it to fetch the process list for us. So we're making some progress here. But remember that ultimately we want to be able to communicate with the server ourselves without any help from Xcode. So that means our understanding of the serialized messages must be perfect, down to the exact bytes. Fortunately, we already have a lot of clues, just from a few well-placed breakpoints. And now it's time to get our hands dirty and dive into the decompilation and refine it until we figure it out. So if we refine the decompilation enough, we can finally complete our picture of a serialized Objective-C message. So we see that each message is broken up into two parts, the header and the payload. And the payload itself is broken up into the payload header, the auxiliary data, and the payload object. The auxiliary data will contain the method arguments. The payload object will contain the method selector or the return value of a method. So now we're finally ready to start sending messages to the server ourselves. So a standalone application called DTX Message Client is also included with the plugin I just demoed, and the source is available for reference for anyone who wants to see it. This app is able to invoke the running processes method in the server, retrieve its return value, and print it to the console in plain text. So let's try it. If we pass it the proc list method, there's our process list without anyone's help. That's great news. That means we can successfully communicate with the server ourselves. So that's fun, but how about a little bit of extra credit? Turns out the running processes method isn't the only interesting method out there. There's something called installed applications, which we've seen before. What happens if we invoke that method? It returns a list of a description of every application that's installed on your device. A lot of useful information in there. There's also a method called launch process. Let's try that. So what I've done here is told the application to invoke the launch process method and passed it the bundle ID of my Facebook app. And we can see that the instrument server launched it with this PID value. So it looks like it launched a process for us, which is great. So let's check if it's in the process list. Oops. And it is. So that's pretty cool. And there's also a method called killPID. Let's try calling that method and pass it the PID of our Facebook app we just launched. And we can see that Facebook's now gone. So this is all pretty useful, right? But we think that we're just scratching the surface here. I mean, we kind of got what we wanted out of it, but the instrument server is responsible for way more than just simple process control. Like I said before, it manages, performance statistics, memory leak checking. I think I'm pretty sure the instrument server actually manages UI automation for automated UI tests on iOS, so you can write your own. You have the potential to write your own iOS automation apps with this kind of framework that we've built. And this DTX message class is also used by other iOS developer tools. So there's a lot of potential here for future work. We kind of got what we wanted, so now we're kind of putting it out in the community for anyone who wants to take the reins and start exploring, what exactly you can do with this kind of stuff. So hopefully this is just the beginning. And that's it, unless there are any questions.
Thanks, great talk. So this basically looks like there's like a custom RPC protocol that is just shuffling across like Objective-C method names and arguments. Right, yeah. And so have you looked into this format for, I guess, one, looking to compromise the server, and two, just seeing if there are any sort of dangerous methods that aren't public but that you can send stuff to and cause bad things to happen?
Well, I haven't looked into it yet, but what I was really hoping was for that exact question. I was hoping for someone to ask, what kind of evil stuff can I do with this thing? So no, I have not looked into it in terms of doing something malicious yet. The most malicious thing I think you can do is that this kill PID method that I demoed, it can actually kill any process on your phone without requiring a passcode, which is kind of interesting. So if you're an iOS developer and you have the iOS developer tools on your phone, and you say, hey, Troy, can I charge my phone on your computer? I can look up any process on your computer and kill it without needing your passcode. So there's already some kind of security questions to be asked here, but absolutely. I mean, there's probably some super obscure internal method buried down in there that Apple way did not expect anyone to call. I just haven't found it yet, so maybe someone else will.
Cool, thanks.
Mm-hmm.
So following on from that, the server, I get this, my intuition is that it's built on top of dtrace.
Sorry, what was that?
My intuition is that the instrument server side, following on from the RPC question, is built on dtrace. Do you have any sense of whether that's true?
Built on dtrace. Oh, probably, but I do not know. I haven't gone that deep into it. I've just basically just done whatever I can to extract what I need out of it and haven't gone very much further. So, I mean, I imagine that you could answer that question if you took a look at, my notes and the slides and the source code, and you'd have a good idea of, how to answer that question. Okay.
No more questions, then thank the speaker again.